Situation 1, notice I am balanced up and down because both forces are 3 newtons. To the left and the right, I'm applying a force and I have this friction of 5, but this is balanced, right? So what's happening then, because it's balanced in both directions, is that the net force is going to be 0. So the net force for situation A is 0. Now here's the thing. I do have friction and I have a force being applied. So this is a little bit tricky and we won't make it this tricky. But I could potentially say, since these are equal, right, but because I do have friction, that maybe this is moving at constant velocity or a constant speed to the right. So my speed is not changing. I'm moving to the right because that's the direction of applied force causing this friction. The difference is I'm just not speeding up. We do have to be careful if this were kinetic friction, like this would be maybe where it would start to move, but in general, because they're the same, I would just say it's constant motion. Now for the next one, up and down, I still have 3 newtons for weight force, which means my normal force is 3, and I have friction. Now for this one, I don't have an applied force, so this is tricky, right? The thing is, if I have this friction working on the object, that means the object is probably in motion, right? Otherwise, I wouldn't have friction. I would just have an object sitting on a table at rest, right, or on a surface at rest, up and down. Because it's friction, my guess is it's moving to the right. So the net force for this is going to only be the friction force, which is going to be negative 5 newtons because it's in the leftward direction. So to describe this one, I would say that this object is moving right and slowing down. All right, for situation C, what I have here is the up and down are both the same. I have no forces working on either side. So what I would say then is the forces are balanced. So I have 0 newtons. Okay, 20 minus 20. And for this one, I would say that this particular object is at rest. Okay, and maybe, again, maybe they don't have the forces on here, and maybe it is moving left and right at constant speed, but because there's no reference to forces, I would take a guess that that one's at rest. And then for the last one here, we have this object, and notice the air resistance is actually more than the force due to gravity. So if I want the net force, I have the positive force, 40 newtons, plus the negative force, so minus 25 newtons. So my net force here is a positive 50 newtons, right? So this means I'm accelerating upward. Okay, so that means I'm moving in this direction, in the positive direction. Okay, let's see. So I guess for something like this, you could think about this as, I don't know, if the air is pushing up, right? This could possibly be like a thrust force, really, where you have a rocket shooting up into the air. So you're accelerating upward, the air is pushing up, gravity's working down. All right, so for number 26, you hit a baseball with a bat. We call the force on the bat the action force. The reaction force, then, is just going to be the bat hitting the baseball. So the baseball hits the bat, right? So the bat against the ball is the action force. Reaction is the ball against the bat. If forces are always equal, how does the object move? All right. Objects moved if the forces are equal. I'm guessing this means that we have balanced forces, right? So an object is moving A equals 0 with constant speed. Okay. So if it's moving, it's already in motion. Okay. A bus has an acceleration of 5.4 meters per second squared. So this one's going to be in red here. Oops. Okay. So we have our acceleration. The bus has a net force of 105, and we want the mass. So that's easy enough. Net force equals mass times acceleration. We're trying to solve for mass. Mass equals the net force divided by acceleration, which is 105, divided by 5.4 meters per second squared. Let me grab my calculator. So for this one, 105 divided by 5.4, and I get the mass is 19.4 kilograms. Okay, and then the last problem that we're going to do is this friction problem here. So here's what we have. We have a 20 Newton force is applied, so that's my applied force, to a 5.2 kilogram book in order to move it across a rough desk. The coefficient of friction is 0.3. So the free body diagram, because I'm applying a force to a book across a rough desk, the desk is going to provide a normal force. I have the gravity force working down, and I have an applied force to the right of 20 newtons, and I'm looking for the friction force. What is the magnitude of the weight force? Well, remember, weight force is just M times G, so that is going to be 5.2 kilograms times 10 meters per second squared. So the weight force here is going to be 52 newtons. Okay, so this equals 52 newtons. Now, if this is 52 newtons and I'm not accelerating up and down, then the normal force must also be 52 newtons. So Fn is equal to Fg because the net force in the y direction is 0. Those forces are balanced. So Fn equals 52 newtons. Then we want to use this equation for friction to find the magnitude of the friction force. So friction equals mu Fn. Mu is given in the problem, 0.3 times 52 newtons, what we just solved for. So 0.3 times 52, the force of friction is 15.6 newtons. And then it says, what is the net force in the horizontal direction? So in the y direction, my net force is 0. In the x direction, my net force is going to be, this is my applied force minus my friction force. Well, my applied force is 20 newtons, and my friction force is 15.6 newtons. So my net force for this problem is 20 minus 15.6, which is 4.4 newtons. So I have a net force working on the book to push it to the right. Using net force equals mass times acceleration, and my answer here for net force, I'm going to solve for acceleration. So my net force equals mass times acceleration. If I divide both sides by the mass, acceleration is net force over mass, 4.4 newtons. They give us the mass is 5.2 kilograms. So the acceleration is 0.846 meters per second squared.